you know if we can turn the lights down slightly?
Oh yeah, lights down?
Yeah. All right, well, today we're going to be building out something called Conway's Game of Life, which is a cellular automata simulation. So it's basically just like, we're going to model these cells by saying, oh, if there's an overpopulation in some area, there's going to be death, and if there's the right number of cells, then we're going to say that it's alive. And then you get some kind of interesting complex properties from those. Except our version is going to be a little bit slower than this. Great. So we have a bunch of cells in a grid, and then the next step, what their state is going to be in the next step, is determined by their neighbors. So a live cell with 2 or 3 neighbors will survive, and a dead cell with 3 neighbors will become a live cell. Oh, no. Shoot. I tried to close the app, but accidentally I closed the screen sharing software. Six.
You uploaded the code.
Hmm?
You uploaded the code.
I did.
In case you're wondering, in the meantime, you can also download the code that he's using right now, also from the textbook. So if you want to do that, you can do that as well.
To be honest, I would suggest not and just taking notes, because there's going to be a lot of extra stuff that's not really important. Like really what you need to get out of here is just the concepts and the syntax, but it's totally up to you. Okay, so here's this diagram again, which has a cell. So we're focusing on the middle cell. The next state is going to be dependent upon its neighbors, which there's these 3 rules that will determine that. And we'll go over those later when it's more important. But so there's these 3 states that we're dealing with, which is dead, and then I split one. So just instead of having a live, we have a new cell and an old cell. And so typically what you would do if you were in Python or Java is you would just create some constants. So let dead equal 0, let new equal 1, and then let old equal 2. That's totally fine. We can do that here. And then we're just going to populate the board. So go from 0 to a width, which is just an arbitrary integer I chose earlier. And then for y in 0 to a height. And then we're going to take this integer board and we're going to assign to it, add an x and y. And this subscript isn't something you need to know. It's something I made just in some of the code that's supporting. So you don't really need to pay attention to that. But so for every cell, I'm going to generate a random float. And then based off of that, it's going to be a certain state. So I'm going to generate a random float, 0 to 1. And then let's say like if seed is less than 0.66, then I'm going to say that we're going to assign something that's dead. Otherwise, if the seed is less than 0.77, I'm going to say it's new. And then for all other cases, I'm just going to say that it's old. So then we can present our board. It's going to look like this. So clearly some randomness, and we have our old cells are white, our new cells are blue, and our dead cells are black. But like a lot of what we talked about last time is how can we make things safe? Because like, for example, if I was not being careful and I did something that didn't make sense, then we're going to have a crash at runtime. So we have this invalid cell type. So this is kind of scary, and it doesn't feel very swift. Like we built out these optional types and things to deal with edge cases, so we don't have to worry about them at runtime. So the way that we deal with this, which is a specific case where we can enumerate like a certain set of cases, is something called enum, short for enumeration. And these are similar to what you'll find in Java, except they're significantly more powerful, which we'll talk about in a while. Yeah.
Could you please make it like a little bigger?
Sure. Is that good? Okay. Okay. So the way that we define this enumeration type is, well, first we give it a name, and it's just this syntax. So we say an enum with a name. So for example, I'm going to be modeling study spaces at Cornell. So there's like Duffield, and for each case, we just write case and then a name. Case Upson, man, I don't know. Some of you guys are crazy and will study in Donlin or PSB. And then, so how do I use this? Because like before I could just do dead and like it would come up. But here we actually have to get it out of the enum type because that's where it lives. You can kind of think of it as like a static variable. So I say like my favorite spot will be study space dot Upson. But there's actually something else we can do, which is if we're assigning to somewhere that expects that enum. So if we're assigning to a variable of type study space, or we're assigning to a function that takes in a study space, this study space is implied. So we can just dot an Upson, and it will assume that we're looking within this type already. And so if you run it, they should show up to be the same. Yeah?
So can you explain the difference between those two again?
They're the exact same. It's kind of like what we were doing with arrays last time. It's just syntactic sugar. They're the exact same. They just look kind of different. Yeah. So now we're going to use, yes?
I have another question. You said that before you could just type dead and it would run.
Yeah.
What is dead?
Dead was a global variable that I assigned at the beginning, just to represent like the dead state, so that we could be consistent. Yeah.
Oh, thank you.
Okay, so now we're going to write this function, which will describe our study spaces. So we'll say if our study space is Donlin, then I want to print this sad thing. And then otherwise, if the study space is Upson, or if the study space is man, and notice how since this equation, the equality here, expects study space on both types, I can just write dot Upson instead of doing study space dot Upson. But of course, you could do the more verbose form if you wanted. Then I'll print out this. And then, of course, for all other cases, you should rethink your life choices. And then if we run this, should hopefully have the behavior we want. Great, it does. But like, we kind of put in a lot more work than before. We create a new type. You'd kind of hope that you could do something a little cooler. And you can. There's something called a switch statement, which is nicer than these if-elses because it'll actually check your work. It'll make sure that you've covered every single case, which is possible because we've listed every single case. So if you notice, we have this study space, and that's kind of like this variable that we're putting into a bunch of closures here to see what my behavior is. So to do a switch statement, we write switch, and then we switch on the variable that we want our behavior to depend on. So we do switch, and then just like the enums, we just fill in cases. So Donlin, and then I put a colon. This is kind of like Python, the way that you'd write that. And then I already have this, so I'm just going to take that. And then the way that we would match two of them, so like how I had the or for before, is you just put a comma in between. So dot man. And you'll notice if I don't cover every case, right, because we still have Donlin and PSB, it'll say switch must be exhaustive. It'll say that I am missing cases, and it will actually fill them in for me. Of course, I want these to be the same behavior. So I could do commas, but like if we had, say, 100 cases, this would kind of suck because I'd have to do 100 cases. So what we do is if you have just something that you want to default to, like something that's everything's going to be the same and I don't want to write out every case, you can just write default. And that's like your else at the end of this statement here. And as I said earlier, these will actually get more complicated. You can do a lot cooler things with them. But for now, this is all we really need to do. Yeah.
there's an underscore at the beginning of describe.
Yeah, sure. So when you create functions in Swift, you have your parameters. So you need a name and a type. And so like if I say my name, it will just print my name. I need a name and a string, and then it will print it. So just print name. If I ever want to call it later, you'll notice that it requires that I pass in this name here. Like I need it to kind of mark my code, so it makes it easier to read. So I'll put in Noah, and it'll print. But like, I don't know, sometimes I get lazy. I don't want to type them out. Or sometimes it just adds a lot of clutter if you have a lot of arguments and you don't want them to be there. So you can just put this underscore here. And what that does is it still names the variable, because obviously you still want access to it. And when you're writing your function, it'll give you a little help. It'll say name. But that means that I can just ignore the type there, or the name there. And so if I had like multiple like things, and then I could just do comma, and then I would just go in normal. Or that would go down here. But yeah, it's just to make it anonymous.
Okay, thank you.
So that's working. So now we're going to apply our enums to our case. So first, we're going to make an enum type. So Conway state, we can call it. And we're going to have 3 cases. So they'll be dead, they'll be new, and they'll be old. And we can kind of spice up our enum to have a little bit more functionality. So for example, if we wanted to convert to work with another program, maybe we wanted to go back to integers later, we can do, I don't know what the proper terminology is for this, honestly. I call it literals. But what you do is, if you put this colon and then a type, it means that you're associating each case with that type. So for example, I can say dead is 0 and new is 1 or old is 2, which is exactly what we had before. And then what I can do later is Conway.dead, and then I can, Conway state.dead. I can pull out this integer later, and it will be 0. And then I can also initialize a case from this integer. And that should be dead. And then if I'm not safe and I do an incorrect input, then it will come up with nil. And so this will actually fill in for you. You don't actually have to assign numbers. You can if you want to. But this is going to still be 0. This is 1. This is 2. It'll go in order for you. So that should stay the same. Great. OK. Now, if you remember, we had colors assigned to our states. So I would like that to be something I can get from the state. So what we can do is create a variable called color, and it's going to be something called the UI color, which you don't have to worry about. We'll talk about it next lecture. And this is going to be something special. So actually, I'm going to change this slightly. So instead, I'm going to create a function, and I'm going to call it color. And so what this will do is it will, if we call it on our state, it'll return a color. So I'll do switch on self, because that's the parameter that we're switching on. So if it's dead, that's going to be self. So if I do my cases. Oh, and note that when you're doing a switch statement, you do need the dot. You can't just write it as you would in the original enum, like here. So, and then I'm going to return a color. And again, you don't need to worry about this, about the color literal. That's what I just typed. Then I'm just going to go, I want dead to be black. I want old to be white. And then I want new to be some bluish color. And then, of course, I can do Conway state.dead.color, and it should return a color for me. Great. So return black, which is exactly what I wanted. So I'm going to change this slightly. So you'll notice that I originally wanted to put this into a variable. And so in Swift, there's a lot going on with variables. You can make them your typical stored properties, or you can do something that's a little bit more complicated. You can do computed properties, and you can add properties onto it. There's a lot going on. We're not going to be talking about that right now, but we do need to talk about computed properties. And a computed property is essentially a function that's just given a variable name. So like, I'm just going to copy this code and put it into color. to the variable. And what this does is every time that I ask for color, it's going to run this function and it will return the value. So this is a get only variable. So should do the exact same thing. Great. And the reason why these are necessary will come along kind of soon. Okay. Back to our diagram. So now that we have like, oh, actually I have to make a board. Sorry. I might have deleted that. Yeah. I think we'll get into that later, actually. So we have this board, right? So we have our cell. And then we're going to need to, for the next iteration, we're going to need to look at all the neighbors and count them. So the way that you could do that is you have a two-dimensional array and you just, run down, or one-dimensional array, and you run down it, and for every single cell you would calculate the number of neighbors, which is fine, it works, but like it's a lot to do, especially if you have like all dead cells. That's like an O of n squared operation, which is just like so much extra. So what we're going to do instead is for all of our living cells, we're going to put them into a dictionary, which hopefully you know what that is. We'll talk about it soon. We're going to put into a dictionary, and then for each thing in the dictionary, we're going to assign counts to the neighboring cells. So for example, if we were doing this one, we'd iterate through all the living cells. So this one is adjacent to it, so we'll give it a 1, and then this one's adjacent to it, so we'll give it a 2, and then this one's adjacent to it, so it'll be a 3, and then 4, and this one isn't close, so it won't matter. So that's where we're heading. So we're going to need to understand optionals from last lecture for this. And for the most part, I think Justin covered it. Hopefully you were able to understand it from the lecture. There's one thing that you do need to know, which is something called optional chaining. So this is, Justin talked about a lot about unwrapping, right? Unwrapping, forced unwrapping, guard let, whatever. Which means you're taking an optional and you're getting the value that's inside of it. But like sometimes you don't really care. Like if an optional is nil, you just kind of want to stop doing stuff. So this is where optional chaining comes in, which is say, so I have my favorite sandwiches, and let's say that I want to get the first thing from it. So I'll do favorite sandwiches, and I'll get the first, which is a property. And you'll notice that this little question mark comes up. And this is something I didn't type. This is something that automatically is put in for you. And what this is saying is, this is an optional value, right? And I don't know if it's going to exist. And if it doesn't exist, I'm just going to return nil. I'm not going to care about this. But if it does exist, then you can do it. And so the return for an optional chain is always going to be optional. So here, optional string. And then first is also actually an optional. So even though you have an optional, it'll just do it once. So it's just one optional. Does anyone have any questions? Great. So now we're going to get into dictionaries. So dictionaries are a mapping from one type to another. So you're like pairing, for example, names to people or something like that. So the way that we declare this, so I'm going to create a variable, which is again my favorite sandwiches. Oh wait, no, it's just favorite sandwiches, sorry. And this is going to be a mapping from strings to strings. So like put in a name, that'll be a string, and then it'll return a string, which is the sandwich. So the way that we instantiate one is just, or an empty one, is just we give it a type, and then we put the empty dictionary. We can also, like last time, just instantiate the type itself. So we could do string to string. And then if we want to initialize it with something inside of it, we can just do Noah, and I don't know. So that is one pairing. And then if you wanted to do another, you would just do another comma and then put the key, colon, the value. So mapping from Noah to Southwest Sub. Okay. So now if we want to get mappings from it, we have to ask if this exists. We'll do favorite sandwiches. And then for getting, we just put these little square brackets and then the key that we want. And it should return the value that's associated with it. And then you could say, Justin, ask if Justin's in it, which it's not. So what's going to happen is it's nil. And this actually happened earlier. where we had some function that returned a nil and then just a string, which is kind of concerning because you want things to behave the same way. We're always asking for the same type, right? That's kind of paradigm that we're going for. And this is confusing, but this is actually a false notion. If we examine the type that's returned here, so we can examine the type of a variable by pressing Option and clicking on it. See, this is actually an optional string. So why this shows up as just Southwest sub instead of an optional Southwest sub is just because Playgrounds wants to look nice. But they're the same. It's still an optional. Yeah.
And for another mapping, how would you build the dictionary using that notation instead?
This is only used for empty dictionaries. So you'd have to put things in later. Yeah. So otherwise, you would just be using types.
And so the reason that, so for favorite sandwiches, is it automatically optional strings, or can you force it to always be a string?
So it's not optional strings. It is literally a string to a string. But the get operation from a dictionary, because keys, so keys can be potentially represent a large swath of things, right? So you don't know if a key exists within the dictionary yet. So that's why it's optional. It's like, I don't know if this exists. Like, you're giving me the right type, but I don't know. So I'm going to return an optional thing. But like, we're still storing it here. And actually, since we have explicit typing here, you can also just delete that typing as well. Okay, so how do I put things into a dictionary? This is very similar. We do it through subscripting again. So I can put in an invalid person and say that their favorite sandwich is a hot dog. Sorry if that's your favorite sandwich. I don't agree with that on a philosophical level. But then if I look at my my dictionary, it is there. And then lastly, you might be scared of optionals, which is really valid. So one thing you can do is just use dictionaries as an association list. So it's a list that pairs keys and values. So you don't have to worry about if something exists if you ask for all of the things that exist in it. So I can iterate through a dictionary. So for pair in favorite sandwiches. And if you examine the type of pair, you get something really scary. But you can do a little thing. So we just do pair has a key and a value property. Value. I'm just going to print them all out. Key, value. And this is kind of what we expect. There's actually something that's even cleaner than this, which is through tuple assignment, which we'll go over soon. So if this is scary, don't worry. You can just do key value, put it in a tuple, and then it'll automatically assign it for you. And it should have the exact same behavior. And then if you want to remove a key value pairing, what you can do is just subscript, put something in with a subscript again, and then just assign it to nil. So this would remove it. Yeah. Any questions? Great. Okay. So there's something a little more going on within dictionary. So if I examine the dictionary type, so this is actually the documentation for the language. And this is pretty scary, even to me who's been doing this for a long time. But what you need to understand is there's a dictionary and it has a key type and a value type, which is something we know. But there's this weird thing that says key is hashable. Key is of type hashable. And this gets into the idea of protocols, which is a more advanced topic, which we'll talk about in 2 weeks. Yes?
Sorry, can you cover how to remove something from the dictionary?
Sure. So if I want to remove myself from the dictionary, I just put a new value into the dictionary. That's nothing. Yeah. Okay. So back to hashable. First, I'm going to just explain to you protocols a little bit. So the first one we're going to look at is custom string convertible. And this is how a protocol looks. So it's just protocol and a type. And you don't need to worry about this too much. But you do need to understand protocols are like interfaces in Java. They describe types. They say this is a minimum basic features that we want. So here, for custom string convertible, it says I have a description, which is a string, and I want it to at least be gettable. You can also have it settable. But this isn't very important. You just need to know, okay, it's asking for this. And so, okay, how do I make something conform to a protocol? How do I make sure that it actually is like adopting this protocol? And this is something we call extensions of Swift, which is arguably what makes Swift like more powerful than the majority of languages, which is something called extension. And extensions allow you to add functionality to literally any type that you can touch. Literally any type you can extend it. So if I were to do Conway state and make it a custom string convertible. So I guess a little description of what custom string convertible means is when we do this little string interpolation thing that Justin showed you last time, is it says, if you're a custom string convertible, let me ask for a description, which is why it had this description parameter. And so now that we're extending Conway state to be a custom string convertible, see this, compiler gets mad at me and says that I'm missing some conformational things for the protocol, and it can add the stubs for me. So this is what it fills in. It needs a description string, which is what we saw before. It needs to be gettable. You could also make it settable, but extensions can't do stored properties. This is why we need computed properties here. So I'm just gonna, I'll show you what happens if we print out a Conway state from before. Pretty chill. It's like most of the way there, but I don't really, Conway state. I don't love that it's lowercase, which, okay, it doesn't matter that much. I'm really just showing this for sake of example. But so again, we're going to switch on self, and for dead, we're going to return the dead string, and then for new, we're going to return new, and then for old, we're going to return old. So now we successfully made our Conway state a custom string convertible. So getting into hashable, if you don't know what hash maps are, that's essentially what dictionaries are. And it's okay if you don't really understand how they work, but ultimately they leverage a function which will convert your keys into integers for improved runtime. So that's what hashable means, is that there's some function that will convert from your keys to an integer. And hash functions are really hard to do, so Swift just does it for you. So for example, if I wanted to make integers hashable, I just say, okay, it's hashable, and then I don't actually have to implement anything. There's nothing I have to do. It's a little more complicated than that later, which we'll see. And actually, there's a little warning here, because all of the basic types of Swift are already hashable. But so that's where we're working towards. We're going to try to make a type that's hashable. And enums, I think, are by default hashable. And if you want to look a little bit into the hash function, you can see, like, say you have a hashable type, you can look at hash value. So that's using the hash function to create a hash value. But so we need types for our dictionary, right? Because we need something that corresponds from the position to the cell. So we need something to represent position. So the first, most basic type in Swift is something called a tuple, which is essentially just an assortment of types. So you can put it in any order you want. You can put any type in it. You just have to be consistent with them. So here I have a tuple of my personal information, which has my name, my social security number, and then yes, which is no. And then if we want to get anything out of this, I can just do thing and then dot, and then it has all of the properties, and I can get it out of it. And I can also assign, I believe. And if I check again, should have changed. That would make sense. Great. And you'll notice that I was pretty verbose with this. I gave everything a name, but you don't actually have to. So I can say let instructors equal Noah, Justin, Kate, Shungo, and then I can put in whatever type I want, but it'll infer the type for me. And so what do I do if I don't have names for my variables or my properties? And so Swift will just give them automatic names. You'll see here. It's just .0, .1. It's 0 indexed. It's just like in getting it from an array, except you put in a number. So if I did that, you know it. And actually, all of these tuples have this number-based indexing system. So if I went back to my personal information, even though I have names for my variables, I can do 0, and that should give me my name. And if you want to name things later, you can do something called casting, which if you don't understand it, that's fine. But if I want to change it, I can do like instructors. I'm going to rename it to have a best instructor, which is going to be a string, and then an OK instructor, which is going to be a string, and then a chill instructor, string, and then baseball man. I don't know if you guys know Shungo, but he loves playing baseball. And I'm going to just assign it to something. Named instructors, and you'll see that I have the names. And not going to lie, this is kind of gross. I don't want to be writing this everywhere. So what we can do in Swift, which you can do this with literally any type, is just rename it. So I'm just going to say, you use the type alias keyword. Again, this isn't something that's really that important. But if you're using tuples a lot, it's helpful. So I'm going to say instructor set is going to be this type. And then I can just call this instructor set. You can actually make these generic, which is kind of crazy. But OK, so we have this tuple, and like we could obviously make this into something that would be great for our dictionary. So let's try and extend our new type, so instructor set, to be hashable. Hopefully this will run. And sadly, there's actually one type constructor that can't be hashable, and that's tuples, because they are very simple, and they don't want to add any functionality to them. So we can't use them. We have to use something a little more complex. So hopefully you guys are familiar with classes. Yes?
Can you use type alias for other functions like arrays?
You can. Yeah. Literally anything.
And all that does is like make it shorter for every time you want to reference it?
Yep, just easier to read, easier to type. Okay, so hopefully you guys are comfortable with classes. You'll see I have a class here. That's a custom key class. And then I also have a struct, which is a custom key class, which you probably haven't heard of. And they both conform to a coordinate protocol. So I'll bring that up because this is something I wrote beforehand. So you'll notice I have this coordinate here. And it is, well, first it's a custom string convertible, so it needs description. Then it has an x and y property and an initializer. So you'll notice this has a description, this has a description, has an x and a y, this has an x and a y. There's a required initializer, which we'll talk about required later. You don't have to worry about that. But this one doesn't have an initializer. And that's because structs are nice, and they will create one for you. It's just going to figure it out. So for all of your stored properties, it'll just say x, and it'll have the same type. So I'll say x is 0, and y is 0. Oh yeah, and this is how you use an initializer in Swift. You just do the type, and then the arguments of the functions for the initializers. Okay, and that ran. But there's a bit more going on here, because like, why would you have two type constructors if there's not, like, what's the point? So first and foremost, you'll notice that this is an NS object, which is basically just like the base like class. Like I think in Python you just do object or something like that. It's just the base class that handles a lot of stuff for you. And then, of course, the NS object is actually both hashable and custom string convertible. So I actually need to override the previous description variable. And I'll also have to do that for functions if I override functions. And you can't do inheritance on structs. Well, you can do inheritance, it's just different. And we'll talk about that again in a couple weeks. But generally speaking, structs are a more memory safe and structured version of classes. So you can't do cycles, you can't do anything stuff like that. But structs are very nice, and we'll see in a little bit why we like them. Yeah. And that's because of the difference between reference types and value types. So here I have a custom key class. So this is a class, and I'm assigning it in 2 locations. You can look at it. It represents to be the same thing. Notice how this is the description. But if I change my class coordinate, and I say the x is 1, then it changes both of them. Because reference types don't store values, they store a reference to the value, right? So what's happening here is I'm creating a custom key class, storing it somewhere in memory, and then every time it's referenced, so I'm putting it here, I store a pointer to that memory. And then when I assign it somewhere else, it's storing a pointer to that memory. Whereas the difference with my struct chord is a value type. If I change them both, or change struct chord, only one will change, because this means every time that I reference it, it's copying the data of the struct into the new place. So they're completely separate. And to be honest, this doesn't matter that much. It's helpful in some ways, it's not helpful in some ways. But it has pretty important ramifications when we're talking about dictionaries. So let's say my reference dictionary, I'm going to put in a custom key class with x coordinate 0, 0, and I'll assign it to myself because I am the center of the universe, clearly. So it assigns Noah, and then if I check if it's in there, you'll see that it is. It's a little gross, but it is in there. And then if I want to get it out later, I'll just put this in again. But you'll notice that this is nil. And hashable on class works weirdly, because you're not hashing the values, you're hashing the identifier. So that means if I create 2 equal classes, they're going to have different pointers, and thus they're going to hash to different values, and I'm going to get out different things. So what I would need to do is actually store this pointer, Noah's location, and then ask for it again later. And this will work. And technically, there are ways around this, but it's really hard. So for example, say I took out NS object, which means I'm not going to override, but I still want it to be hashable. It's going to give me this error. And then I'm going to have to implement a bunch of stuff, and then it's basically not going to work. And just for the interest of time, I hope you can just believe me on that. Whereas if I do this same process with structs, so I'm going to change this to a custom key, and I'm just going to do it again. Since it is hashing the values, oh, yep, that makes sense. Since it's hashing the values, it should come to the same value, or same hash value. Great, so that works. So we're going to be using structs for the rest of the lecture. So I'm just going to use what we've done and generate a new board. And you'll notice I'm using cell state instead of Conway state. It's literally the exact same thing, except I defined it over here before lecture. Hopefully this runs. Great. And we can look at it again, and it looks pretty similar. So now we have to actually implement the logic.
First, we need to implement this function, which will calculate the number of neighbors that a cell has. And we're going to do this by, again, iterating over current cells and then telling those neighbors that they actually have a neighbor. So we're going to iterate over the board, and we're going to take a pair, which will be the location of the cell and then the cell state. And if you'll notice in the attention, it says that a dead cell can be either nil or dead. So we need to handle this dead case because it's not going to show up in a nil because you can't iterate over nil things in a dictionary. So we say that if cell is dead, then we basically want to exit this iteration because it doesn't matter. We're not counting this neighbor because it doesn't exist. So then to do this, we just do something called a continue, which essentially says if I'm in a loop, just skip to the next loop or to the next iteration within that loop. So we'd handle this dead case. And now that we know that we have a living cell, we need to tell all the neighbors. So we're going to first get an offset. So for x in -1 to 1, and then for y in -1 to 1. And then every time that this inner loop is run, we want to tell a specific neighbor with this offset that it has a neighbor. But first, of course, if it's 0, 0, the offset is 0, 0, then we're telling ourselves that we have a neighbor, which doesn't make sense because we are not a neighbor to ourselves. So if x is 0 and y is 0, then I want to do this continue again. But otherwise, I want to tell this counts dictionary that I have some information I want to check. And so since this is originally an empty dictionary, this means that we need to handle both cases where there's nothing stored and cases where there's something stored. So first we'll do where something is stored. So we're checking if there's any count at a particular location. So we'll do counts, index this location, and as I said earlier, the location is going to be the original location of the cell that we're iterating over. So location, actually I'm going to change this to position so it's a little more clear what's going on. So position.x and then position.y, and then we have to shift it. So plus x plus y. So we say if there is some count at this location, then I want to assign at this location, so counts index location, is going to be the exact same thing, but one more. But if nothing exists at this location, so it's going to return nil, then we need this little else branch. And then we're going to say counts index location, and we're just going to assign that to 1. And that is our counting neighbor function. It's pretty simple. Now we need to actually implement the logic so we can get all of the cells that have some number of neighbors and then decide what their next state is going to be. So we're just going to iterate over counted neighbors, which is going to be this dictionary. So it's going to be a location to an integer. So say location to neighbor count, yes, in counted neighbors. And then all of our changes we're going to be storing in a new board so that we have persistence, so we can look at the previous board if we wanted to later, because that'll be helpful for when we're showing them. Okay. And then again, we have to worry about dead cells being dead or nil. And then we have 3 cases that we need to implement. So I'm going to use a switch statement. You could use ifs, but switches are nice because I can handle all of my cases. And you might remember that we're only switching over one value. So this is concerning because I need to check both the current state as well as the number of neighbors. But we can just create a tuple, and so we'll have both of these in the same thing. So we'll have a location. Oh, no, not a location. We're going to have a neighbor count. And then instead of location, we're going to look at the board's position, or the state at the position. So board index location. And then we have our cases. So first we can do our dead case. So if the count is 3 and the state is dead, or the count is 3 and we have a nil value, then we want to assign at this location to new board, we want it to be a new cell. Next, this is kind of a long one. So we say if a living cell, so new or old, has 2 to 3 neighbors, then we're going to make it old. So we can say 2 and old, or 3 and old, or 2 and new, and 3 and new, a dot here. And I just put this on a new line just to show that it's kind of a different case, but this isn't necessary. And then so new board location is going to be old. And then for all other cases, we're just going to say new board location is nil. We could say dead, but it'll actually be a little better for us later if we do nil. And so now I'm just going to kind of iterate over it. So we're first going to take this first frame. So I'll say like last frame, and this will be what we use for recursion. We'll say custom board, which is what we generated earlier. And then we're going to have a list of images. So I'm going to say frames is, and then the way that I'm making images is this one function called present, but this isn't something that's very important. And then I'm just going to iterate 20 times and say frames dot append. And first I actually need to update last frame. So last frame is going to be the next board of itself. And then I'm going to append it in here. And then I'm just going to create something I call a sequence, which is just something that will scroll through a bunch of images, frames. And then if I run this, I have to present here. Custom manager present my last frame, because it needs to be the same type. And we'll see it starts running. And we'll see, so first it counts our neighbors, and then it counts, or it updates the states, and then it goes back to count the neighbors, and then it should update the states. This is kind of slow, but we're 2 out of 20 times, so it'll be there relatively soon. You can just take a quick breather. Great, so we have a working Conway's Game of Life, and it's not, very much, and it's pretty slow, but it's working. It's clearly there's some stable areas, and there's some very unstable areas, and there's some very complex ones. But I think what's important to note, like I realized there's kind of a lot there at the end that's hard to pay attention to, but what's really helpful to take away is this idea of I have a dictionary, and I'm going to be checking if there's something there, and if there isn't something, I'll just do this like kind of starting value. But if there is something there, I'm going to just reassign it with a slight change. And this is less important, but for those that are interested in switch statements, because they can get quite a bit more complicated, which we'll see down the line, is we can simplify expensive cases like this, or not expensive, but complicated ones with expressions. And in this case, it's actually not that simplified, but you can imagine, say, if I needed to cover 2 through 15 and for all old and new, that would be quite a lot of cases to write. And so in these cases, we can actually simplify it. So the idea is I'm going to assign an identifier, because if I were to try to access these values here, we have no way of doing it. So I'm going to assign an identifier to the number, and then I'm just going to say that it's old or new, because I don't really care. And then I can say where. So this is saying this case will apply if and only if this expression that I'm about to write works. So I can say if count is 3 or count is 2. So this will work when it's old and the count is 2 or 3. And then I could do this and then change this to new. It's still a little bit gross. So we can simplify this a little bit. So we can say an array of 2 and 3 contains our element count, or not contains our element, but you know, it contains a count. And then I actually originally had it like this, where I changed it to new, which this works. And you do have to write a where clause if you're doing multiple cases on the same case. But actually something that would probably be a little bit cleaner would be to let state. So I'm binding the state here and then the count here, where this is true, and dot I might, since this is not you know, guaranteed to be this is not guaranteed to be a Conway state, I actually need to write the verbose one. Actually, this is a cell state, because I kind of lied a little bit at one point. Cell state dot new dot contains state. Now I'm going to just indent. I think I'll put it here because this is a little bit gross. Then hopefully if I run it again, I'm going to only do like 5 frames because I don't want to take it forever. But if I run it again, should hopefully work. Sorry, it might be a little flashy because the frames will iterate or show really quickly and then it will reset. I'm just going to shut the view. And yeah, look, it works again. So that's the second lecture. Hope you learned a lot.